Hello everyone, I'm Yucheng Zhao from University of Science and Technology of China. I will talk about our recent work, Streaming Video Model, in this video. This is a joint work with Chongluo, Chuanxin Tang, Dongdong Chen, Noel Kotler, and Zhengjun Zha. Video understanding is a fundamental research topic in computer vision. There are mainly two kinds of tasks, one of which, named sequence-based tasks, aim to understand what is happening over a period of time. And the other, named frame-based tasks, aim at capturing the detailed information at a certain point of time. Given the divergent inputs these two tasks deal with, separate model families have been developed independently. In our study, we introduced a novel video model paradigm, termed the streaming video model. This new approach can efficiently tackle both kinds of tasks using a unified architecture. To better comprehend this, let's first delve into traditional video models. Clip-based models constitute one type. They take in 3D video clips and output spatial temporal features for sequence-based tasks like action recognition or video captioning. 3D convolutional neural networks had a heyday in the past decades, and now with their rise in video vision transformers. However, despite their extensive study and applications, these clip-based models fall short for many video applications due to the necessity of inputting the entire video clip. As a result, most frame-based tasks like video object segmentation or multiple object tracking adopt frame-based models to glean per-frame features from video stream. These models treat videos as they would images, neglecting any temporal-related information. So, as we observe, both clip-based and frame-based models come with their sets of limitations, rendering them ill-suited as a versatile and effective model for video understanding. In this work, our proposition is a unique kind of video model, the streaming video model. It employs a unified architecture that proves advantages for all existing video understanding tasks. The streaming video model employs two critical innovations to circumvent traditional model limitations. First, we have a two-stage design. The streaming video model accepts a video stream as input. This input format is reminiscent of a frame-based model, except here we maintain and utilize the temporal relations of agent frames. The initial stage emphasizes extracting detailed spatial features within each individual frame. These spatial features are also amplified by a temporal-aware mechanism, making them more representative and robust than those derived from a simple image model. These Stage 1 temporal-aware spatial features serve frame-based tasks like multiple object tracking. The second stage employs a temporal decoder to aggregate video-level spatial temporal features, used for sequence-based tasks like video action recognition. The second significant innovation in the streaming video model is the temporal-aware spatial encoder, achieved via streaming T2D attention. Given an input feature xc, the streaming T2D attention first calculates the standard intraframe self-attention within each frame. Subsequently, we maintain a memory pool to store historical information. During each frame's forward process, we incorporate the keys and values from the self-attention into this memory pool. Hence, in the forward pass of the first frame, the memory pool contains only the keys and values of that frame, and in the forward pass of the T frame, the memory pool stores all keys and values from past timestamps. We then compute the interframe cross-attention between a newly generated temporal query QT2 and the stored keys and values from the memory pool. For this, we leverage the T2D attention to enhance efficiency. The details of the T2D attention mechanism can be gleaned from the reference below. Combining the two-stage design with the temporal-aware spatial encoder, we developed an efficient and effective streaming video model. It accepts a video stream as input and outputs features useful for all kinds of video understanding tasks. In our experiments, we initially focused on the multiple object tracking. The key distinction between our streaming video model and the traditional frame-based model used for this task is the introduction of a temporal-aware mechanism. We therefore conducted two sides of experiments to gauge the effectiveness of temporal information. In the first, we compared the streaming model with the frame-based model on the MOT17 validation set. It's evident that our proposed streaming model significantly outperforms the frame-based model across all metrics compared. In the second experiment, we analyzed whether a longer temporal memory improves results. As depicted in the red figures, extending the test time memory length considerably enhances the tracking performance. These two experiments demonstrate that temporal information plays a vital role in frame-based tasks like MOT, and the streaming video model performs better in such tasks compared to the frame-based models. Next, we carry out further experiments on video action recognition. We used two datasets, Kinect 400 and something V2. We found that our streaming model consistently outperforms the frame-based model on both benchmarks. Interestingly, the streaming model achieved similar top-line accuracy on K400 as the clip-based model. This suggests that our proposed streaming video model might have the potential to supplant clip-based models in sequence-based tasks. In summary, we proposed the idea of streaming video model that aim to unify the treatment of both frame-based and sequence-based video understanding tasks, which in the past were handled by separate models. We also present an implementation named the Streaming Video Transformer and conducted comprehensive experiments on multiple benchmarks. Experimental results demonstrate our proposed model achieves remarkable performance on both action recognition and multiple object tracking. To the best of our knowledge, our work is the first deep learning architecture that unified video understanding tasks. Thank you for your listening. For more detail, please read our paper.